In 1970, a young physicist at Yeshiva University was staring at an equation about subatomic particles when he realized something impossible. Particles, electrons, quarks, photons, everything we thought were tiny points in space, they're not points at all. They're strings, one-dimensional objects vibrating like guitar strings, creating every particle in the universe through their different vibration patterns. Leonard Susskind thought he'd made a mistake. That's insane. Particles can't be strings, but the math was undeniable. And what he didn't know at the exact same time, two other physicists on two other continents had reached the exact same conclusion. This is the story of how string theory was born. To understand why this discovery shattered everything physicists thought they knew, you need to know one thing about Leonard Susskind. He wasn't supposed to be here. He grew up in the South Bronx in the 1940s and 50s. His father was a plumber. Nobody in his family had ever gone to college. When young Lenny told his dad he wanted to study engineering, his father said something that changed his life. "You ain't going to be no engineer. You're going to be Einstein." That quote, half joke, half prophecy, stuck with him. Susskind went to City College of New York, then Cornell for his Ph.D. By 1970, he was a professor at Yeshiva University in New York, working on one of the biggest mysteries in physics, the strong nuclear force. Here's the problem physicists were facing. Inside every atom, you've got a nucleus, protons and neutrons packed together, and inside those protons and neutrons, you've got quarks. 3 quarks in a proton, 3 in a neutron. But here's the weird part, you can never pull a quark out, ever. Try to yank one free, and the force holding it in gets STR the farther you pull. It's like a rubber band that never breaks, it just keeps stretching, requiring more and more energy. This phenomenon is called quark confinement, and in 1970 nobody understood it. The standard model of particle physics said particles are point-like objects, zero size, no internal structure, just mathematical points with mass and charge. But if quarks are points, why can't you separate them? Susskind was working on a different but related problem, understanding how particles scatter off each other at high energies. An Italian physicist named Gabriel Veneziano had discovered this beautiful mathematical formula, the Veneziano amplitude, that described these scattering processes with incredible accuracy. But nobody knew which way it worked. It was just this mysterious equation that fit the experimental data, and that's where Susskind comes in. He was sitting at his desk at Yeshiva, staring at Veneziano's formula, trying to understand what physical object could produce this pattern. And then it hit him. Before we get to Susskind's breakthrough, you need to understand just how radical his idea was and why everyone before him had missed it. For centuries, physicists had been breaking matter down into smaller and smaller pieces. You take a rock, you get molecules. Break those apart, you get atoms. Split the atom, you get a nucleus and electrons. Crack open the nucleus, you get protons and neutrons. And by the 1960s, physicists discovered that protons and neutrons are made of quarks. The whole story of particle physics had been go smaller. Find the next fundamental point particle. It was like Russian nesting dolls. Each layer reveals a tinier version inside, and every physicist assumed the pattern would continue. Quarks were probably made of something smaller, and that something would be made of something smaller still. All the way down to what? Infinitesimally small points, mathematical abstractions with zero size. But there was a problem with this picture, and it was becoming impossible to ignore. When you collide particles at high energies, like in particle accelerators, strange things happen. The number of particles you can create seems infinite. Smash 2 protons together hard enough, and you don't just get quarks. You get dozens of other particles flying out, mesons, baryons, resonances, each with different masses, different spins, different properties. It's like hitting 2 billiard balls and getting a slot machine jackpot of particles. Physicists cataloged these particles. They organized them into families. They found patterns in their masses and spins. But nobody could explain why these patterns existed. Why do particles come in these specific families? Why do their properties follow these mathematical relationships? And then there was the Veneziano amplitude. In 1968, Gabriel Veneziano, working at CERN, discovered a formula that described how particles scatter off each other. It wasn't derived from any theory. He just found a mathematical function that fit the data, but it was beautiful, elegant. Too elegant to be an accident. The formula had a strange property. It exhibited what physicists call duality. The same scattering process could be described in two completely different ways, either as particles exchanged in a direct collision, called the channel, or as particles exchanged indirectly, called the T-channel. These two descriptions should be separate, but in Veneziano's formula they were the same. It was like having two different routes to a destination that somehow occupy the same road. Physicists were baffled. What kind of object could have this dual property? Point particles couldn't explain it. If you model particles as points, you get one description or the other, channel or channel. Not both at once. The math doesn't work. Some physicists started thinking maybe we need to give up on the idea of fundamental particles entirely. Maybe everything is just interactions and forces with no real objects underneath. But that felt like giving up on 400 years of progress. And that's where things stood in 1970 when Leonard Susskind started working on the problem. He was at Yeshiva University, relatively young, relatively unknown. He'd been thinking about the strong nuclear force, the force that holds quarks together inside protons. And he was staring at Veneziano's amplitude, trying to reverse engineer what kind of physical system could produce this equation. Think about how you'd approach this problem. You've got a mathematical formula. You know it describes scattering particles, but you don't know what the particles are. It's like someone hands you the blueprint for a sound wave and asks you to figure out what instrument made it. Piano, guitar, violin. Susskind started playing with the math, and slowly something started to emerge. The realization came gradually, then all at once. Susskind was working through the mathematics of Veneziano's amplitude when he noticed something strange. The formula had a structure that reminded him of something from his undergraduate quantum mechanics classes, harmonic oscillators. A harmonic oscillator is just a physics term for anything that vibrates in a regular pattern, a pendulum swinging back and forth, a mass bouncing on a spring, or a guitar string vibrating after you pluck it. In quantum mechanics, harmonic oscillators have a specific mathematical fingerprint. They come in discrete energy levels like rungs on a ladder, and Veneziano's formula had that exact same structure, but not just one harmonic oscillator. Infinite oscillators, an infinite ladder of energy levels, all stacked on top of each other. What in the physical world has infinite harmonic oscillators? Susskind thought about it. A single vibrating object, like a guitar string, has infinite modes of vibration. You can pluck it to produce the fundamental note, or you can make it vibrate at twice that frequency, or 3 times, or 4 times. These are called harmonics, and there are infinitely many of them. Could the Veneziano amplitude be describing a vibrating string? At first, Susskind dismissed the idea. That's ridiculous. Particles are points, not strings. Everyone knows that. But he kept working through the math, and the string interpretation kept getting stronger. Here's the key insight that changed everything. If you imagine a particle not as a point, but as a tiny string, maybe 1035 meters long, far too small to see even with our best microscopes, then different vibration patterns of that string would appear as different particles. A string vibrating in its fundamental mode might look like an electron. A string vibrating in the first harmonic might look like a quark. A string vibrating even faster might look like one of those mysterious heavy resonances that physicists had been cataloging. All the particles, the entire zoo of mesons and baryons and resonances, wouldn't be different objects. They'd be the same object, just vibrating differently, like how a single guitar string can produce different notes depending on how you pluck it. And the duality that made Veneziano's amplitude so mysterious, suddenly it made perfect sense. A string has two ends. You can describe an interaction from the perspective of one end or the other end. S channel and T channel aren't different processes. They're the same process viewed from different perspectives. Susskind worked through the mathematics and everything clicked. The infinite ladder of particles, the mass relationships, the patterns in their spins. It all came from the string vibrations. He'd figured it out. Particles aren't points. They're strings. In his documented recollections, Susskind has described the moment with characteristic directness. He thought he'd made a mistake. The idea seemed too strange, but the mathematics was undeniable. But here's what makes this story even more remarkable. Susskind wasn't alone. At the exact same time, completely independently, two other physicists were reaching the same conclusion. Yoichiro Nambu at the University of Chicago was working through the same problem and arrived at the string interpretation from a different angle. He was thinking about how flux tubes in quantum field theory might behave like relativistic strings. And Holger Nielsen in Copenhagen was doing similar calculations, also realizing that Veneziano's amplitude described stringy objects. Three physicists, three continents, three independent discoveries of the same idea. None of them knew about the other's work until after they'd published. This is actually how the biggest breakthroughs in physics often happen. When an idea's time has come, multiple people stumble onto it simultaneously because they're all looking at the same clues. It's less like a single genius having a vision and more like a lock that suddenly has multiple keys, because the lock was always there, waiting for someone to notice the right shape. Susskind published his paper in 1970, Structure of Hadrons Implied by Duality, in Phys.Rev.D. The title is technical and understated, typical for physics papers, but the content was revolutionary. He'd just invented string theory. And he'd done it by taking a mathematical formula that nobody understood and reverse engineering the physical reality behind it. Think about that for a second. For 3 centuries, physicists had been breaking matter into smaller and smaller pieces, always assuming the fundamental building blocks were points. And in one paper, Susskind said, "What if we've been wrong the entire time? What if the universe is built not from points but from strings?" When Susskind published his string theory paper in 1970, the physics world didn't quite know what to do with it. This wasn't a case of immediate rejection or fierce opposition. It was something more subtle, cautious interest mixed with deep confusion. The mathematical structure was beautiful. Nobody disputed that. But what did it actually mean? Nambu, Nielsen, and Susskind had all independently shown that strings could explain the Veneziano amplitude and the zoo of resonances in particle physics. But there was a massive problem. The math only worked in 26 dimensions. 26 dimensions. Not the 4 we experience, 3 of space, 1 of time. 26. Some physicists thought this was evidence that string theory was just a mathematical curiosity, not a real description of nature. Others started working on how to hide those extra dimensions. Maybe they're curled up so small we can't detect them, like how a garden hose looks one-dimensional from far away, but is actually a cylinder. And there was another problem. The theory predicted a particle that didn't seem to exist, a massless spin 2 particle. Most physicists saw this as a flaw. The theory was making predictions that didn't match reality. But then something remarkable happened. In 1974, John Schwarz and Jodl Shirk, 2 theoretical physicists working on string theory, realized something that everyone else had missed. That troublesome massless spin 2 particle, it wasn't a bug. It was a feature. It was the graviton, the quantum particle of gravity. String theory wasn't just a theory of the strong nuclear force. It was a theory of quantum gravity. It unified gravity with the other forces of nature. It was potentially the theory of everything that Einstein had dreamed about. This realization transformed string theory from an obscure idea about hadrons into one of the most important research programs in theoretical physics. Susskind continued working on string theory through the 1970s. In 1974, he and John Kogut published a paper showing how color flux tubes, the stringy connections between quarks, lead to quark confinement. The rubber band holding quarks together isn't just an analogy, it's literally a string. But the real explosion in string theory came in the mid-1980s, what's now called the first superstring revolution. Physicists discovered that string theory wasn't just one theory, it was 5 different theories, depending on how you formulated it. And all 5 avoided certain mathematical inconsistencies that had plagued earlier attempts at quantum gravity. Suddenly, every ambitious young theoretical physicist wanted to work on strings. Edward Witten, widely considered the greatest living physicist, led much of the charge. String theory went from obscure to dominant in less than a decade. By the 1990s, Susskind's 1970 insight had spawned an entire field, thousands of physicists working on strings, extra dimensions, and quantum gravity. His original paper on hadron duality has been cited thousands of times. The idea that seemed crazy in 1970, that particles are vibrating strings, became the foundation for modern theoretical physics. But Susskind himself didn't rest on this achievement. He kept pushing forward, discovering the holographic principle, fighting the black hole war with Stephen Hawking, proposing the string landscape. String theory was just the beginning. If string theory is correct, and that's still a big if, then everything you think you know about particles is wrong. That electron orbiting the nucleus of an atom, it's not a point. It's a loop of string vibrating in a specific pattern. The photons carrying light from the sun to your eyes, strings, the quarks inside every proton in your body, strings, the gravitons that in theory carry the force of gravity, also strings. The entire universe is made of tiny vibrating loops, each 1 trillions of times smaller than an atom, each vibrating in a different pattern to create the particles we see. It's as if reality is a cosmic symphony, and every particle is just a different note played by the same instrument. This has profound implications. First, it means there's a fundamental length scale in nature, the string length, about 1035 meters. Below that scale, the concept of point breaks down. You can't have infinitely small objects. Everything has a finite size. This solves a lot of mathematical problems in physics that arise from treating particles as true points. Second, it unifies all the forces. In string theory, the different forces of nature, electromagnetism, the weak force, the strong force, and gravity, all emerge from different vibration modes of the same strings. They're not separate phenomena. They're different aspects of the same underlying reality. Third, and this is where it gets really mind-bending, string theory requires extra dimensions. Depending on which version you're working with, you need 10 or 11 dimensions for the math to be consistent. Those extra 6 or 7 dimensions are supposedly curled up at every point in space, too small to detect. But they're there influencing how strings vibrate and thus determining what particles exist. And fourth, string theory suggests that the fabric of spacetime itself might be emergent, not fundamental. Space and time might be like temperature or pressure, large-scale properties that emerge from the vibrations and interactions of strings. This is still an area of active research, and Susskind himself has worked on this question extensively through his holographic principle research. But here's the thing, we still don't have direct experimental evidence for string theory. The strings are far too small to see directly. The energies required to probe them are millions of times higher than what our most powerful particle accelerators can achieve. So how do we test it? Some physicists have proposed indirect tests, looking for subtle signatures in cosmological data or in the properties of black holes or in the results of high-energy particle collisions, but so far nothing conclusive. This has led to one of the biggest debates in modern physics: is string theory even science if we can't test it? Critics, like Lee Smolin, who's written entire books attacking the string theory research program, argue that it's become untestable speculation, more philosophy than physics. Susskind's response has always been direct: the math is too beautiful to be wrong, and absence of evidence isn't evidence of absence. Just because we can't test string theory todai doesn't mean it's unfalsifiable forever. The debate continues. But what's undeniable is this: Susskind's 1970 insight fundamentally changed how physicists think about the building blocks of reality. And there's a direct line from that first paper on vibrating strings to his later work. The holographic principle, his most famous idea, actually grew out of string theory. He realized that strings growing larger as they gain momentum was connected to information being stored on surfaces rather than in volumes. The matrix model he developed with Banks, Fischler, and Schenker in 1997 was a way to formulate string theory in terms of quantum mechanics of matrices. His work on black hole information used insights from string theory to argue that information is preserved. String theory wasn't just one discovery. It was the foundation for 5 decades of research and counting. Leonard Susskind is 86 years old now. It's been more than 50 years since he sat at his desk at Yeshiva University and realized that particles might be strings. In that time, string theory has gone from a wild idea that 3 physicists independently discovered to one of the most studied areas in all of theoretical physics. It's been declared dead multiple times. It's been hailed as the theory of everything. It's inspired thousands of papers, launched countless careers, and fundamentally reshaped how we think about reality. And we still don't know if it's right. That might bother some people. 5 decades of work and we still don't have proof. But Susskind has never been bothered by uncertainty. His entire career has been about pushing into the unknown, asking questions that make other physicists uncomfortable, and following the math wherever it leads. From a plumber's son in the South Bronx to one of the architects of modern theoretical physics, the story of string theory is also the story of Leonard Susskind himself. A person who looked at what everyone thought were the fundamental building blocks of nature and said, what if we're wrong? What if there's something deeper? And maybe that's the real lesson here. The universe doesn't care what we think should be true. It is what it is, and sometimes the only way to understand it is to let go of everything you thought you knew and follow the mathematics into territory that seems impossible. Particles aren't points, they're strings, and that changes everything.